Hi, I'm Tianlu. I'm glad to share our work, Efficient RGBT Tracking via Cross-Modality Distillation. RGBT tracking is the task of estimating the state of an arbitrary target in each frame of an RGBT video sequence. Due to the affordability of the thermal infrared sensors, RGBT tracking draws more and more research interest. Most existing RGBT tracking models first adopt a two-stream structure to extract multi-level unimodal RGB and thermal features respectively. Then employ elaborate designed multimodal feature fusion modules to exploit complementary information within multimodal data. We call such a tracker as powerful RGBT tracker, but these powerful RGBT tracking models usually require high computational costs and large model sizes. Differently, a compact RGBT tracker adopts a single-stream feature extractor with fewer convolutional layers and employs simpler multimodal feature fusion modules. They inevitably bring performance degradation. Now, the research question becomes, can we shrink the RGBT tracker without sacrificing performance? This paper answers these questions using knowledge distillation, which allows a compact model to obtain a similar ability of a complex model at a little cost. A cross-modality distillation framework is presented to bridge the performance gap between a compact student model and a powerful teacher model through three stages: unimodal feature extraction, multimodal feature fusion, and target state estimation. Proposed CMD framework includes a teacher model, a student model, and three knowledge distillation modules. The knowledge from the teacher model is transferred to the student model to mimic more effective feature representation. The architecture of the employed teacher and student models, which are both based on recent Deep RGBT Tracker DIMP, and the teacher model employs the multimodal feature fusion modules in the previous RGBT Tracker MFNet. In the stage of unimodal feature extraction, the proposed specific common feature distillation module first performs cross-modal interaction on the unimodal RGB features and TIR features from the teacher model to highlight the modality common information and the modality specific information at different layers. Firstly, the proposed specific enhancer modules are employed to obtain such modality interacted features with more modality specific information via subtraction and multiplication in shallow layers. Then, for the RGB and TR features of deep layers, the proposed consistency enhancer module is employed to obtain modality interacted features with more modality common information via addition and multiplication. Besides, inspired by the idea of knowledge review, we employ a series of attention-based fusion modules to adjust the channel dimensions of unimodal features and dynamically aggregate the cross-layer features in the student model. Finally, the modified features of the student model from the ABFICs and the modality interacted features of the teacher model will be employed together to force the student model to mimic the specific and common information from the teacher model via proposed feature learning distillation laws. In the stage of multimodal feature fusion, in order to learn exploration ability of complementary information from the teacher model more effectively, we design a fusion module by using multiple fusion strategies donated as a multi-path selection distillation module. The proposed MPSD module first performs multimodal feature fusion from three typical perspectives: modality differences, modality commonality, and modality complementary. After that, these initial fused features are combined together by a weighted fusion way. With the fused features obtained by the teacher model and the student model, we calculated the fusion distillation loss. What's more, in order to enable the student model to adaptively select a fusion path that is more similar to the teacher model in different scenarios, we introduce an additional penalty for the efficiency of knowledge transformation during training. We first find the type of initial fused features, which is more similar to the fused features in the teacher model. Lambda I denotes the selected type of initially fused features. Then, through the adaptive selection part in MPSD, the student model itself will also predict a type of initially fused features that is suitable for the current training scene. Gamma I denotes the predicted type of initially fused features from the student model. After that, We can use a penalty to help the student model to choose fusion paths that is most suitable for the current scene under the guidance of the teacher model. By minimizing LP, gamma and lambda I will tend to be consistent, which can enable the student model to select the fusion path according to the teacher model. In the stage of target state estimation, to alleviate the data imbalance problem, we propose a hard-focus response distillation module to instruct the student to focus on distinguishing targets from the hard negative samples. Firstly, we use a Gaussian-shaped mask RG constructed background truth bounding box to correct the response map of the teacher model RT. Secondly, the student model can focus more on distinguishing target from the hard negative samples by proposed hard-focus response distillation loss. We conduct some ablation studies on RGBT234 to discuss the impacts of different components in our CMD framework. In Table 1, impact of each component in our proposed CMD are verified. In Table 2, severe variants are also compared with our proposed SCFD module. In Table 3, severe variants of our proposed MPSD module are also conducted to verify its effectiveness. We also compared our method with some existing state-of-the-art RGBT trackers. In addition to the teacher model, our method achieves the best results in most datasets. This demonstrates that our proposed method can effectively reduce the performance loss caused by parameter reduction.